All right, so video over molecule shape and how it relates. This video will mostly just be the molecule shapes, and then I'll try to introduce a little bit about polarity of those shapes towards the end. Okay, I don't want this to be too long, right? Probably a second video on polarity, and then of course a video on intermolecular forces, why these things matter, if that makes sense. So I got this little simulator pulled up. Okay, and this simulator is the PhET simulator. PhET has a lot of great simulators. This one specifically is, guess what? Molecule shapes. And very useful because, molecules are, get this, three-dimensional. And it's kind of hard. A lot of people struggle with visualizing things in three dimensions. Okay, so this tool hopefully helps you see what's being described. Okay, so with molecule shapes, all right, the basic idea is you have some compound, right? This, you'll notice there's no elements, right? It's purple and white, right? It could be anything. But the premise is that molecule shapes are going to be exclusively for compounds, okay? How bonded things, how the bonds are, for lack of a better word, they're geometries to each other, aka if you look at this molecule, right, you're like, oh, there's two bonds and they appear to be opposite each other. Specifically, you would say, oh, these two are 180 degrees apart. Meaning, right, if I try to jiggle this bond, right, you'll notice the other bond tries to get away. You get too close and it's like, ew, get away. And hopefully you're saying, oh, because there's electrons in the bond and they don't want to be near the other electrons, do they? And that's exactly the reason. Okay, this what we're describing, and I'm not a huge vocab person, as you guys have probably noticed, but you might as well know the name. This is called valence electron shell repulsion theory. Repulsion theory. Okay, and basically what's happening here is the electrons that are in the valence shell, the valence layer, do not want to be near each other because they're both negatively charged, right? This is a Coulombic repulsion. Two negatives don't want to be near each other. Two positives don't want to be near each other. Okay, that is basically what this is. Okay, if that makes sense. And again, I don't really care if you know what that is, right? Sometimes we call this like VSEPR. Okay, it's fine if you're like, do I need to know that? Nah, not really. Okay. The big deal here is, oops, that's not the button I wanted, is that this tells us the shape of a molecule, and that is very important, okay, or it will be very important for us, okay? So for right now, if you look at this and say, well, what shape is this? If you click on here, it says molecule geometry. This is linear, okay? And you're like, well, yeah, it's a line, linear. Can't really draw it any other way, can you? Because these things do not want to be near each other. So the best angle you could have here is 180. You say, why not 181? Well, 181 is better on one direction, but then the other direction is getting too close, right? 180 is diametrically opposed. You can't get further apart than that. So that's the ideal angle, ideally. I had to say it in there. Okay. Now, that sounds great. And yeah, hey, linear, cool. All molecules linear. Well, no. Because if I add something else to the atom or to the molecule, for example, a third part of my compound, three things attached, we call these substituents. Okay, these three things now, again, there's repulsion. And that repulsion is, I don't want to be near the electrons. But here's the problem. I can't be diametrically opposed because there's somebody else in the way. Okay, once you have three things, you really can't be linear anymore. Okay, three things attached, that is. All right, so this shape, you might notice, is what's called trigonal planar. And trigonal, because it kind of makes a triangle. Planar, because if you look at this, it's flat. It's in a plane, okay? AKA, you could call this maybe the XZ plane, right? Maybe a little bit easier to picture would be like the XY plane, right? Going across and up, right? It's flat, though. There is no, for lack of a better word, there is no third dimension here. It would look flat to you. Okay, obviously the atom has thickness, right? It is three-dimensional, but it doesn't appear to be like this, right? It's not sticking out up or down, if that makes any sense. Okay, so if you keep adding stuff, you'll see that they change. Put a fourth one on, And now we have what's called a tetrahedron. Okay, a tetrahedron. Tetra is the Greek word for four. Hedron means like face, basically surface. Okay, a tetrahedron has four sides, and you might notice the angle now between all of these things to each other is 109.5 degrees, which again is the best angle we can get in this case. This shape is most certainly three-dimensional because now we have something coming. If you think about this, this is coming out at you. This is coming out of the screen at you. Okay, this one's coming up. This one's kind of going back into the screen a little bit. This one's going back into the screen to the left a little bit. This is three-dimensional. And this shape is the optimal way to separate these bonds. Okay. Now you got to realize this is assuming these are all equal, aka everything attached is the same element. All right. If you change this guy to some other element, these angles could change a little bit, and we'll talk about why. All right. But this is like an idealization. It's still a tetrahedron. Okay. Even if you did change one of them, but the angles might not be exactly 109.5. Okay. So let's just add more, just so you can see. Right, adding a fifth one, this is going to make what's called trigonal bipyramidal. Okay, and if you're like, whoa, trigonal bipyramidal, what's going on? Think of it as a triangle, right? If I look at this, it makes a triangle, and it makes a pyramid. If I'm looking from the top down, right, this is the top of the pyramid going down, that is a triangular base. So it's trigonal pyramidal, but it's not just trigonal pyramidal, it's bipyramidal because there's a second one, right? Bi means two, right? So we have this second pyramid sticking out of the bottom, we'll call it, okay? And that would be trigonal bipyramidal, 5 things attached. The last one you can have, so to make things simple, because it doesn't go on forever, would be a 6th substituent, okay? This is often called a octahedron. Okay, this is basically 2 tetrahedrons that have been stacked on top of each other. So tetra's 4, 2 of them is 8. Okay, and this is basically, to make things simple, the biggest you could make. Okay, or rather the most complex one you can make. Octa, 8 sides. Okay, and if you look at it, you're like, oh yeah, so we have this square base now. Okay, and this would form kind of like a pyramid, right? Sometimes this is called square bipyramidal, a square base pyramid. Okay, and there's 2 of them, kind of like the trigonal bipyramidal. But, you know, a lot of times it's just called octahedral. So why make it too complex? Notice the angle is 90 degrees. Okay, again, that's the best we can get. That's the biggest distance we can get. Okay? Now, if you say, all right, well, that's the biggest, cool. You know, what about these other bonds, right? Well, if you put a double bond, right, or a triple bond, right, it still has the same behavior. It's still going to be, in this case, there's 3 things, trigonal planar. However, in the real world, these bonds are going to push a little more than this single bond, okay? So this is an idealization. In the real world, it can change. Hopefully that's making sense, okay? The other piece to this puzzle, and you may have noticed this, you may have been like, hey, what about those? What about the lone pairs? Lone pairs are when you draw a molecule. When I say draw, I mean a Lewis structure, right? Remember Lewis structures, right? Hopefully you remember those. A Lewis structure is a way to represent how the atom, or how the molecule, I should say, exists. So if you had, for example, carbon dioxide, right? If you draw out, we'll do it the long way. Here's your Lewis dot diagram of carbon. Here is your Lewis dot diagram of oxygen. There's 2 of them. It's CO2, right? So we would have something that looks like this. 6 valence electrons, 6 valence electrons, 4. You say, oh, they want to make bonds to be happy. So here's a bond. Oh, there's going to be a double bond here, right? Oh, there's going to be a double bond here, right? And everybody's happy. So we take this and we draw it a little bit neater. Right, instead of circling it, we make lines. The lines are the bonds. Okay, so it would look like this. If you drew this, it's mostly right, but you're forgetting about these electrons. So we include those. Those are the lone pair of electrons. Okay, these guys are sticking out in their own orbital. Okay, to make things simple, these are sticking out, kind of just hanging out there. Okay, they're not bonded, right? But they are, they're there, and they have negative charge, right? So they're hanging out, okay? This is carbon dioxide, okay? And if you look at this shape, hopefully you're like, I think that's linear, right? 2 things attached, probably linear. And in this case, you'd be correct, Okay, in this case, yes, CO2 is a linear molecule. If I were to take a very similar looking molecule, very similar, we get a different shape because of lone pairs. So let's take a look. If I asked you to draw me SO2, sulfur dioxide, you would say, oh, that's pretty similar looking, isn't it? So I have sulfur. Sulfur is going to look like this, right? 6 valence electrons, just like oxygen. Okay, so now if we draw this molecule, okay, just drawing this out, it's going to look something like this. We're going to have a bond here, okay? We're going to have a bond here. I know you're probably like, wait, but that's a pair. I know. The idea of pairing it is more where the bonds prefer to start. Okay, so do the singles first. So, hey, that's a single, take that, and then we'll take this, okay? Hopefully that's making sense. The oxygen is going to get what he wants because he's more electronegative, right? Sulfur is mildly electronegative. Oxygen is the second highest. Only fluorine hasn't beat, okay? So you say, okay, I got that. I draw my Lewis structure. What does it look like? You say, okay, that's a double bond to the oxygen. That's a double bond to the oxygen. And then you say, oh, my lone pairs. Let me not forget those. So oxygen still has these. This oxygen has those. And critically, right, sulfur has these left over. And that's really important. So on the center atom, notice I don't really care about these lone pairs. You should draw them because they're there, right, to be thorough. They don't really matter, though, at least not for this. Okay, they matter, just not for this. On the center atom, though, they're going to matter big time. These electrons, they're hanging up there. They're hanging out. And guess what they do? They are going to repulsion. They're going to repel the electrons in those bonds. So you got to think of it now like if my head is the sulfur's lone pair of electrons, right? And my arms are the bonds. Picture it as these negative electrons have a lot of power, very strong negative charge. There's nothing really mitigating, nothing lessening their charge. It's going to cause the bonds to press down, push them away, okay? And that makes it not linear. That will change its shape. And that's really, really important. So if I draw this, like let's do SO2, okay, 2 double bonds, it should be linear, you say, but don't forget the lone pair. And when you add the lone pair, it changes this angle. And now we would call this a bent molecule. I mean, bent is pretty obvious. You're like, oh, it's a line that's been bent. Exactly. Okay. A bent molecule has very different properties than a linear molecule. Okay. And again, that we'll get into the next video. All right. So if you're like, why? Hold on to that question. It's a good question, but it will be very important. Okay. So with lone pairs, let's kind of go through those just so you can understand them. Okay. Given an atom or given a molecule, right, given a compound, you can draw the Lewis structure. And based on where the lone pairs or how many lone pairs there are, it's going to change the behavior, okay? So if you have one thing attached, it's going to be linear no matter what, okay? I add all those lone pairs, it does not affect the bond. And if you say, why not? Well, they're all pushing on this, right? But it's always going to be 180 degrees, okay? I don't care if it's sticking out like this, like this, like this, like this. You know, compared here to here, this angle, okay, to the other atom is always going to be 180. Okay, it's always linear if there's one thing. If you put two things in, right, we assume linear. You put one lone pair, that's bent. You put two lone pairs, it's still bent. You put three lone pairs, now it's back to linear. And you're like, whoa, but you got to think about why. These are more powerful, and they want to be further apart from each other. They are, how do I put this nicely? They're like, ew, another lone pair. I want to be as far away as possible from here. So notice here, they take this angle here, which basically pushes them further apart than, say, these guys. These guys, because they're weaker, they got to get closer. Okay, the angle here is going to be a little bit bigger than that 109.5. Add a third lone pair, and now the angle they take to each other, right, is that 120. That's the biggest angle they can take, right? And that incidentally forces these guys to be diametrically opposed again, okay? Add a fourth lone pair, and we have the same thing now, okay? So think of it as trying to get these things as far away as possible from each other. And there's limitations with the orbitals, okay? Again, chemistry Not that we're lying to you when we teach you this stuff, but there's other things going on than just that. Okay, the valence shells can get complicated when you get to d orbitals and stuff, but don't worry about that. Okay, so anyway, let's get back to this. So you say, okay, cool. Two things, we are basically going to be linear bent always. Okay, what if you have three things? You say, yeah, that's trigonal planar. If I had a lone pair, I want you to think, where is it going to go? It wants to be as far away as possible from everybody else. He's the king. He's going to be, get this, on top. When I say on top, by the way, it really, there is no top to an atom. You can rotate it, right? But if you think about it, he's kind of on top. He's like the king, the crown, right? And he is going to force those bonds down. And this, hopefully you're looking at this saying, that kind of looks like a pyramid. Exactly. This is trigonal pyramidal. So you remember trigonal bipyramidal, two pyramids. This is one pyramid, okay? If we're looking just at the molecules. If you say, what about the electrons? What if we include them? Well, then you can think of this as a tetrahedron, right? But we would not call the molecular geometry. We're ignoring. Imagine like if I remove the lone pair so you don't see it anymore, that looks like a pyramid, okay? So like NH3, ammonia, would be this because of that lone pair, okay? That lone pair is powerful. It has a humongous impact, okay? What if we had another lone pair? This one hopefully you can kind of picture really easily. This would be what's called T-shaped. Because guess what? It kind of looks like a T, right? And you can picture here that these lone pairs, again, are trying to separate themselves as far away as possible from everybody else, and it forces these atoms to have a 90-degree angle. Okay, so these lone pairs are further apart, angle-wise, and then these substituents, these three other elements, or three other things attached, I should say, they will form this 90-degree angle to each other, which creates, again, kind of like a T-shape. Okay, so there's be three things with two lone pairs. Okay, if you had one more lone pair, right, there's not a better configuration. Okay, it's still going to be T-shaped. Again, for my high school chemistry, I am not going to make you memorize all these. I just think it's important you see that the shapes can change, okay? And the shapes changing will have impacts on polarity, okay? But I would highly encourage you to play around with this simulator because it'll hopefully help you understand why some molecules are polar and some are not, okay? So anyway, that's three things, right? Let's do 4, tetrahedron. If you add a lone pair, now we have probably the most funny one, the seesaw, which, it looks like a seesaw, right? You can see here's like the legs and here's the little parts you would sit on, right? It goes up and down, right? It's a seesaw shape, okay, because that lone pair says, everybody get away from me, and this angle configuration is best for him, and everybody else has to deal with it. Okay, so that would be a seesaw. What if you had another one, right? Now we have a really cool one called square planar. Trigonal planar was 3 things attached, right, with no lone pairs, made a triangle that's kind of flat. This, because of these 2 lone pairs diametrically opposed, puts these guys in a 90-degree flat angle to each other, which means we make a square, right, a flat square. Okay, again, this square planar. Okay, so like xenon tetrafluoride, for example, would be a good example of this. Okay. Okay, what if we already have the lone pairs? Again, notice we really can't go over 6. Okay, and there's a reason for that. All right, even going to 6 is a lot of electrons being used in a bond or just around an atom in the valence shell. This is pretty difficult. A lot of atoms can't do it. There's only a handful that can really do this easily. But anyway, so 6 is kind of the magic number. Anything above 6, just we don't worry about it for this class. Okay, so that's 4 things. What if I have 5 things, right? We know that's trigonal bipyramidal. Add a lone pair to this. This makes this square pyramidal. And if you're like, why? Well, take a look. Square base, and that is a pyramid, right? Good old Khufu, which is the big pyramid in Giza, right? That's the big pyramid everybody thinks about, right, in Egypt, would be this shape, a square pyramid. Okay, square pyramidal. And again, it's because that lone pair is like, ew, everybody get away from me. And this would be the best configuration, okay? Again, we have 5 things, so I can't add another lone pair after that, right? That makes 5 plus 1, 6, okay? Which means having a 6th thing, I can't add lone pairs. There's nothing after that. So those are the shapes, all right? And the trick is this. You're taking a quiz, you're taking a test, whether it's my class, whatever. You can't just pull this up and go, oh, the answer's octahedral, right? Because that's not you thinking. That's just you basically just say, hey, computer, what's the answer? It's can you draw it, right? Can you draw the Lewis structure? And can you understand why that would separate these things. And just one last piece on this is how we draw these, right? You can't draw three-dimensional things on 2 dimensions, right? But you can find ways to kind of visualize it or virtually create 3 dimensions. So for example, if I drew methane, methane is CH4. Okay, methane, carbon with 4 valence electrons, 4 hydrogens. This is going to be a tetrahedron. Okay, 4 bonds of carbon with no lone pairs. That's a tetrahedron. 4 sides, no lone pairs, right? The way we can draw this is we could say, hey, there's a hydrogen coming out the top. We could say then there's a hydrogen kind of coming back into the wall, back into the computer screen this way. We could say that there's a hydrogen kind of coming out this way, and then we could say there's like a hydrogen coming out at you, right? And this kind of gives you that three-dimensional aspect, right? To make it a little bit easier, like once you draw this out, you can kind of make it look nicer once you have all 4 things. So I might put, oops, that's not what I wanted. I might redraw this one, make it look a little neater. Oh, I did it again. Oh boy, I keep undoing it. I gotta stop right-clicking. I guess right-clicking is Control-Z by default. Anyway, it will look something like this, right? So it's kind of coming down into the screen, down out of the screen, and then just down along the screen, right? Makes it look 3-dimensional. And hopefully you're like, oh, yeah, that's kind of trigonal pyramidal, or sorry, that's kind of like a tetrahedron, right? 4-sided thing. Okay. If you have access to a molecular modeling kit, right, little ball and stick things you can put together, that also really helps. Okay. But I really think the best way is this simulator, very helpful. And then once you feel comfortable with like fake elements, fake as in like this is not a real element, right? There's just balls. You could switch over to this, real. And then it would tell you, okay, so for water, H2O is a bent molecule because of the lone pair, right? You say, what about sulfur hexafluoride? Well, that's going to be octahedral, right? It has 6 things attached. It has to be octahedral to make it simple, right? Hey, what about BF3? It's got 3 things. Is it going to be trigonal planar or is it going to be trigonal pyramidal? Well, boron only has 3 valence electrons, which means it's going to be trigonal planar. Whereas ammonia, NH3, has 5 valence electrons. So those 3 get used, we have 2 left over, which is going to make that trigonal pyramidal. Okay, so that's what I'm saying here. Okay, you need to kind of play around with these. And the name of the game is the Lewis structure. You need to be able to draw the Lewis structure. If you don't draw the Lewis structure, you just have to memorize every single one, which is absurd. That would be crazy. I would never expect you to do that. So learn, or rather refresh on your Lewis structures. Other than that, that'll be this video. So have a great rest of your day.